Okay, let's start. Hello, everyone, and welcome to the fourth day of the Swampland School. We are here to, sorry, I can't.
Sorry,
okay.
Yeah, okay.
This is the last lecture by Thomas Van Riet. Thank you very much, Thomas. Please go ahead.
You're welcome. Yeah, okay, thank you. So if you remember where we ended yesterday, then we motivated with supergravity calculations the Sitter Swampland conjecture. There is, of course, more than one de Sitter Swampland conjecture, but this is the original one, which applies in the asymptotic regime of field space. So you should think intuitively that it is something that applies in taking the supergravity limit, but should also apply a little bit before. Otherwise, I mean, the Swampland criterion should be rich enough so that it also says something about string theory in a non-classical regime. And the criteria or the Swampland conjecture I have not discussed, but I think Lars might have discussed them in the other lectures, is the TCC bound. So I will not discuss that one, but the TCC bound should be, you should consider it as a generalization of the Swampland bound that applies also, say, in the middle of field space, where the theory can be strongly coupled, etc. Okay, so what I promised you to give to start this lecture with would be to present some heuristic arguments in favor of this. Why? I don't think one should take them per se too literal, these arguments. I think they should rather represent the kind of flavor of thoughts, lines of thought that go in, which could sort of justify these arguments. So I think none of them are, how do you say, waterproof, but they at least are indicative. Okay, and it's of course very interesting to try to study them deeper and try to see whether one can make the arguments actually much better. Okay, so what I will do, so the original paper by Oguri, Shiu, Palti, and Vafa, they relied on the distance conjecture and on using the interpretation of the cosmic horizon area as an entropy. I will instead describe a shorter and alternative proof by Hebecker and Raza, which appeared in 2018. Okay. So what it relies on is actually rather simple, only on two things. Okay, so in a similar spirit, it relies on the distance conjecture. So let me recall you the distance conjecture very quickly, because I think you have been discussing this in the other lectures. The distance conjecture says that when I go to an asymptotic regime in field space, there is a tower of states that is becoming light as an exponential of the field distance. Okay, so here phi would be some canonically normalized field. And how exactly it becomes lighter, you know, it's not specified, but it should be sort of exponentially with some factor b, which is not really specified and could be situation dependent. So that's one thing that the heuristic argument uses. And the other ingredient is what is called the species bound by Dvali et al. In case you haven't heard of the species bound, let me just very quickly mention what it is. So the species bound is supposed to tell us that the cutoff of a gravitational theory can be significantly lower than the Planck scale in case there are many fields, in case there are many species, particles. All right, so there is a naive argument by Dvali that if I have, you know, if the number of species is large, and we call it n, then the cutoff of the theory is lowered by m Planck over square root of n. Okay, I think the message here is that sort of the effective, you know, expansion parameter for, you know, loops, etc. I mean, that's sort of very hand waving. Instead of, you know, going like 1 over m Planck, you can think of it as, you know, a new m Planck given by this value. Okay. Right, so these are the two ingredients. So what is it saying? I go far away in field space. There's a tower of light modes. And at the same time, this really changes the cutoff of the theory by the species bound argument. These are the two arguments. And of course, if you put the two together, you can actually get somewhere. So how do we relate this to cosmology? Let us do this right away. So one thing you can do with these two equations, you can manipulate them. And what one can try to get out is to eliminate n, okay, the number of species. And how do I eliminate them? Well, I use a distance conjecture, okay? And to make my life easy, I'm going to assume that the tower of states is equally spaced. So what is then the number of particles? Well, it's a cutoff divided by the distance between two spacings, which is the characteristic mass scale of the tower. So this is our number of species, right? So I have an equation for n here, I have an equation for n here, and I can eliminate n. And if I do so, I find this relation, that the cutoff of the theory goes like this: mass spacing m times m Planck squared to the power 1/3. So you see that this is indeed a mass scale. And then I rewrite this equation by saying, well, little m is of course given by mp times the exponential fall off. So I find the following relation, all right? I still have not made contact with cosmology at this point. The only thing I've done is, which was trivial from the start, if you just mention what is a species bound, you mention what is a distance conjecture, it becomes clear that the species bound must simply relate to the distance in field space, and that is a formula I just derived. Okay, at this point now we will make contact with cosmology. How? First of all, by observing that there is a relation between the scalar potential and the Hubble radius according to the following formula. Okay. This is the dimension full scalar potential, so it has mass dimension 4. And I'm using also the fact that if I want to be in my effective field theory, I better have that the Hubble scale is below the cutoff of the theory. So H has to be smaller than lambda, or I am completely out of control. What I mean is that there would be no effective field theory description of cosmology, so we would not be able to talk about an effective potential nor about scalar fields. All right, so now it's easy. The only thing I do is I combine these two equations. So I rewrite this inequality, or I take the 4th power of this, depending on how you want this, and I plug in what is lambda. And of course, I find an inequality for my potential. So this is the main argument. What do I see? I see that whatever the potential for my field is, it is bounded by an exponential fall off. In other words, if I go far in field space, V at least has to fall off like an exponential, okay? And indeed, this is always true. But you can be confused, you say, but wait a minute, in all of the previous lectures, you wrote down the scalar potential was always some polynomial in rho and tau. I agree with this statement, but again, this when you use a distance conjecture, it's crucial. You talk about the right kind of distance in field space, and here it is measured with respect to a canonical scalar field. Rho and tau of the previous lectures, when I translate them into terms of canonical scalar fields, they are in fact exponentials. Okay, so we already observe that in 3-level compactifications of 10D supergravity with sources, indeed, all scalar potentials are sum of exponentials. So in asymptotic regime, they're nicely, just some exponential function going down. Okay, so that is, you could say, maybe this is a heuristic explanation of why this happens in 10-dimensional supergravity, because 10-dimensional supergravity knows about string theory. String theory should know about, UV completion and all of these non-trivial pieces of physics. Good. Also note, this is heuristic. Clearly, there's only one field in this argument. You can think about making this more precise, etc. But that is not the point of my lecture. Now you can wonder, okay, does this rule out the sitter? As I tried to explain you last time, and I started my lecture today saying this, that is not true. This conjecture, from the arguments, you see it's only supposed to hold in asymptotic regimes in field space. For the middle of field space, there is an argument, which is called the TCC, which I invite you to look at this paper, but I will not discuss it. Okay. So this, yes.
May I ask a question?
Of course.
It's not. So this that you use, I would expect the force root of potential is bounded by lambda, not h itself. So it's just a matter of order one difference in the exponent. But why you choose h less than lambda, not the root of potential less than lambda?
Good point. You're asking. Right. Okay, I think, let me try to reformulate your question so that I am sure I understand it, okay? So you're saying if I have a certain cutoff, let me call it lambda, why am I asking that h is smaller than lambda? Because I could also ask, well, let me think about the energy density. And then the energy density would be square root of h and Planck smaller than lambda. Is that correct?
Yes,
I agree with this. Yeah, that is for sure correct.
Square less than lambda to the 4.
Right. Yeah. Well, depends on which, whether lambda is dimension mass or mass to the 4th, etc. Exactly. Yeah. So I agree with this statement, and so that would be another bound. But the reason I use this one is for the following reason. So h would set a length scale. It's literally the geometric length scale of the universe. It's the Hubble scale. Okay. So this is a distance at which I do my cosmological observations. That distance, that length scale better be not above the coarse graining scale at which I'm allowed to, sort of make experiments or make statements of my effective field theory. So that's another way of looking at it, right? But I understand your question, sure. And I think it's a valid point, like should you do this? I think this is a valid thing to do, but I do appreciate your point. And this is what I mean with heuristic. At all of these levels, you can always say, it's not waterproof, and I agree on this statement. This is, again, a flavor of the kind of ideas that could lead to these statements.
Yeah,
But
because
yes.
on the other hand, we are tempted to regard H as some kind of IR cutoff, which is definitely smaller than the UV cutoff in the
Yes, absolutely. So some people would have said this: I want my IR cutoff to be below my UV cutoff, or there's no room for my effective field theory to live in. And that's another way of indeed having this equation. Absolutely. Thank you.
Thanks.
Okay, so what did I do? I now want to say, okay, we are done a little bit with the sitter. So let me recall you. First lecture, I gave some basic principles of flux compactifications. The second lecture, I applied them, and I at least discussed the case of the sitter in asymptotic regimes, and I now finished that part by giving heuristic explanation. Okay, and now I come to the last part of my lecture, which this should be the third lecture, therefore. This is asking myself about something that is less phenomenological, but it's still close to phenomenology, and that is a question of scale-separated ADS. What does that mean? Okay, so remind yourself of holography, all the holographic backgrounds we know. People use the word ADS-CFT, and as Kumrun Waffa likes to complain, that word is wrong. And I fully support this statement because it confuses people. There's not a single string theory example where ADS is dual to a CFT. Not a single. The only things we have in string theory so far are examples where you have ADS-N cross some compact manifold, which is dual to a CFT. And that is important because this compact manifold at no point can be ignored in describing the CFT. It is absolutely crucial to get the CFT correct. In fact, most of the times, all of the details of the CFT all depend on the details of this compact manifold. And one of the reasons is that in the actual computations or in the actual backgrounds, the volume scale of this manifold is the same as the Hubble scale of this ADS space. And this I explained in the beginning of my lecture. When you would put an observer in one of those spacetimes, the observer says spacetime is 10-dimensional. Okay. So what about phenomenology, right? So I think if we are really fair and we listen to mainstream media and they talk about, oh, string theory predicts a landscape of vacua, sometimes people throw this word 10 to the 500 vacua. What they really refer to is something like the original KKLT paper, and you don't have to think about uplifting to the sitter. Okay, so the breakthrough of KKLT at the time was not only full moduli stabilization, because that would not have been enough. No, the breakthrough, which is sort of underemphasized in the paper, this was the first time where moduli stabilization was achieved in a almost phenomenological fashion, meaning that the ADS space that they obtained was far greater than the size of the compact dimensions. So it's the first time in which you could say, here is an ADS space in string theory for which there is an effective field theory description. You understand, right? So ADS5 cross S5, we often say, oh, that is described by SO6 gauge supergravity in 5 dimensions, and I disagree. That is a consistent truncation. That is not the effective field theory of ADS5 cross S5. The effective field theory of ADS5 cross S5 is 10-dimensional string theory or 10-dimensional supergravity. Okay. So this was a major breakthrough of KKLT. So in other words, what they obtained was that LKK over LDS, they were able to make that number become very, very small. All right. And in a way, it had to be from the start. Why is that the case? I mean, if you take any textbook or paper, famous paper on string phenomenology, you will see that 99% of these papers are not doing full string theory computations. What they are doing is they're somewhere between top-down research and bottom-up, which does not necessarily pose a problem. There's nothing wrong per se with using effective field theory, but you need a self-consistency argument in order to apply it. For instance, for KKLT, which I will quickly review soon, what you're saying is, okay, I have 10-dimensional string theory, and then I have an instanton effect. But this instanton effect is really more argued using 4-dimensional physics, but then you have to make sure that you can apply reasoning from 4-dimensional physics. And for that, the extra dimensions better be small. So what KKLT argues is, okay, let us assume that we do a calculation, and then we check at the end whether indeed that assumption was correct. This is how you should think about this. These are self-consistency arguments, okay? Good. So what I will do now, I will again go through this very simple exercise of rho and tau scaling and discuss scale separation from that point of view. So I will do this classically, and then I will go to the quantum regime. And then the lecture will be over the moment I've made contact with the Swampland conjectures. So as before, but now I've done it for general D. Here is a compactification of 10 dimensions to d-dimensional space with a 10 minus d-dimensional compact space. Rho is the volume in string frame. And here I wrote this typical tau variable. And now I will be a little bit careful. I will work with lower dimensional Planck units. You remember my discussion? So I keep the VEV of the field. So there's tau 0, which is the VEV of tau. And then there's tau to the minus 2. So in the vacuum, this factor drops. But when you consider fluctuations, this thing is not trivially there, okay? It's a nice exercise to show that if you want to go to 4-dimensional Einstein frame, tau to the d minus 2 equals e to the minus 2 phi, rho to the t minus 2 over 2. Okay, if I now compactify 10-dimensional supergravity, I will find the following action. I will find Einstein-Hilbert term, and in front of the Einstein-Hilbert term, there's a factor tau 0 to the d minus 2. Again, tau 0 is the stabilized value of tau. So you read off that indeed tau has a very simple interpretation. It is the Planck. Did I make him? No, I didn't make a typo. This is the Planck mass. All right. Good. So this also means when I write a symbol V here, I write Planck mass to the power d. It means that I'm now discussing the dimensionless scalar potential. Good. Let us now, in this language, which we already developed, think about scale separation, what it could be. Well, one proxy for the Kaluza-Klein scale, which you might actually disagree, which I'm fine, is that you say, well, the third power of this guy. Sorry, if I'm like in, let me take the case d equal 4, this is a 6-dimensional manifold, then the third power of this guy would determine the volume. So rho would be like the length squared of the internal dimensions squared. And that is true in every dimension. So I could say, why don't I think that the Kaluza-Klein scale squared is always equal to the stabilized value of rho. That is not entirely fair. Why? What would be the real definition of the Planck mass, or the Kaluza-Klein scale? In fact, it should be really the masses of the particles, which we would discover in accelerators. Okay, so you should rather think of eigenvalues of some generalized Laplace operators on the compact space. But you could think as a proxy, I'm going to use the volume, and you have to be careful, realizing that this could be a bad proxy, but let us nonetheless do it. Okay. Then the lower dimensional Einstein equation, in any case, equals d over d minus 2 times this value. So we read off that once I have an ADS vacuum, V is negative. I should have put an absolute value here, my apologies. Then we read off that the ADS length scale equals a Planck to the minus 2 equals Planck mass to the power 2 times the negative on-shell value, the positive, like the absolute value of the on-shell V, where V was dimensionless. Okay, so this is a true statement, always true. This is always true. It's just this guess of the KK scale, which we can debate. If I nonetheless take it for granted, I can try to compute the ratio, which will tell us whether a solution is scale separated or not. If I just fill in all the details that I've given you here, M Planck should be filled in. Here is the formula. That should be L squared KK, that's rho 0. So indeed, you see that you have to multiply rho 0 times tau 0 squared with the on-shell value of the scalar potential. If that thing goes to 0, imagine you can achieve that. You actually found a solution with scale separation. So this is great. This is a very simple formula. And since we're playing all these games with rho and tau, we can actually check whether that is a possibility. Okay, you don't need much technology for this. So I'm immediately, of course, going to show you the example where people were able to do it. Okay, so I'm telling you, okay, instead of type 2b, I'm going to try type 2a. And let me even try a Calabi-Yau geometry or 6 planes F0, H3, and F4. Let us take those ingredients. And let me remind you that if it's Calabi-Yau, it's Ricci flat. And there is a bound on these 3 numbers. There's a bound on the number of orientifolds because of topology. There's a bound on F0 and H because of the tadpole condition, which I already discussed before, right? So F0 and H are not fluxes which I can send to infinity. But the one I can send to infinity is F4. Because F4 has the following Bianchi identity, but this combination is 0, assuming there are no 5 forms, because there are no 5 cycles, and there are no O4 or D4 branes in my model. Okay, so any closed or co-closed flux will obey the equations of motion, and I can send that flux quantity to infinity. Good, let us see what the effect of that could be. So you could ask yourself, Thomas, why do you send something to infinity? This I explained before. If you want to get something like a parametric behavior, you need to send something to infinity. Okay, and the only thing I can see here that I can send to infinity is the F4 flux. Good, so what is the on-shell potential? We discussed this so many times now. That's this formula, and I don't need to show it to you. I get 2 conditions, which we derived many times before. And now I'm going to manipulate a little bit different than I did last time. And I mean, you know the drill by now, so we just go through it. And the final formula we get is that V equals minus 4 over 9 V4. So indeed, the only vacua possible in this model are anti-de Sitter. If there is 4-form flux, if there is no 4-form flux, I might get Minkowski space solutions. Okay, so let us try to hunt for ADS solutions. So what I'm going to do is I'm going to define my flux quantum of F4 over some 4 manifold, and I call it n. And n is some integer, which I'm going to send to infinity. And now I'm going to use the following trick. If I send this to infinity, what does that mean? It means that U4 goes like n squared goes to infinity. Okay. Now, realize the following. I have assumed that I can make the potential stationary. In other words, I can balance various ingredients against each other. How is it ever possible if this term is going, this coefficient is going to infinity, like n squared? Well, what must be is that if a potential is stabilized in some asymptotic regime, it can only be the case if all of these numbers are equal or proportional to each other in size. Okay, it cannot be that I say that one term goes like n to the -5 and the other term like n to the -6. That is impossible because then they cannot balance against each other. Okay, so I have to find out whether this is possible. So I know, okay, whatever is going to happen, my tau will scale like some power of n. I call it n to the 8, and rho will scale like some power to the, like n to the power b. And the only thing I do is I fill these powers in this expression, and I'm assuming that UH, U0, and O6 are not scaling with n for exactly the reasons I told you before. They are bounded by the tadpole. All right. This is non-trivial, right? Let us count. We have 1, 2, 3, 4 terms. And what I'm asking is that all of these, and we have 2 variables. We have 2 unknowns, A and B. And I'm asking now that the powers of n are all the same. So this is an over-constrained system. You have to be very lucky that this can be done, and it can be done. I invite you, fill in b equal 1/2, fill in a equal 3/2, and you see that all these powers are the same. So this is magic. And of course, the secrecy about this magic is that I took a system which is actually supersymmetric. Okay, but at this point, you should just say, wow, this is great news. Who knows, we can do it. Okay. And imagine it works. Well, v goes like n to the -3/a, which indeed is a negative power. So v will go to 0. If I just fill in these numbers, I can even compute that rho 0, tau 0 squared, v goes like 1/n, and that goes to 0. But you remember what I said about this condition, right? That's exactly the condition measuring scale separation. So it means that I actually found a system in which scale separation could happen. But that's not enough. You have to be lucky for other reasons. You say, wait a minute, I was using 10-dimensional supergravity. Let me quickly check whether everything is under control, right? So I need to check, is my string coupling small? Are all volumes and length scales getting large? So that is obvious because I just showed you here that the ADS length scale gets very large. The volume gets very large. But what was non-obvious, whether I go to weak coupling, let us check it. I just use the definition. I plug in, the scalings with A and B. And I get that e to the -2 phi goes to infinity, so e to the phi goes to 0. So this is great. This is very good news. So once you do some exercise like this, that's when you say, okay, let me actually try to find a solution. So this is what I can advise in research. Imagine you want to achieve something. You first do the simple test. Do I have a playground in which maybe I can achieve this? You do something like this. And then you set up the machinery of, Calabi-Yau compactifications and so on. Right, and this is what DJKT did in 2005. These are the Wolf, Girvayets, Kachru, and Taylor in this nice paper. And what have they shown? They said, look, people, this actually works. We found very explicit SUSY and non-SUSY ADS4 cross Calabi-Yau 3 vacua with all moduli stabilized as well. Okay, that was a very impressive paper. The fact that these things were possible. And the way they did it is they relied on n equal 1, d equal 4 supergravity formulas, using things like T duals to the Gugo-Fafa-Witten formulation, etc., etc. Okay, now you should ask yourself, great, does this mean that we can do it? That string theory has scale separated ADS vacua? Well, there's a catch. What is a catch? The catch is exactly this phrase. It uses n equal 1, d equal 4 Sugra formulation. Are we sure this formulation is consistent with string theory completely? Well, in a later paper by Acharya et al. In 2006, they actually said, let us at least try to check whether we can solve the 10-dimensional supergravity equations of motion. And what did they notice? Oh, we can, on the condition that the orientifold plane sources are smeared out. What does that mean? I talked about this before, that whenever I have a delta function, I replace it with a finite form. So one example would be this equation. I have the Bianchi identity for F2. F2 is magnetically charged on the node 6 plane. So there is, dF2 equal F0 H3 plus delta Q, where Q is the charge of the orientifold planes. And they showed, well, the equation I'm actually solving when I lift the n equal 1, d equal 4 supergravity to 10 dimensions is this equation. dF2 equal F0H3 plus this Q, but now the delta became the real part of the holomorphic 3 form. And this is an example of a smeared source. Okay, so we knew this was a distribution, but it was in fact a 3 form distribution. So it's a 3 form that is singularly peaked. And what they show is that the solution you're actually writing down has a 3 form which is completely smooth. Okay, so that is not a full solution. And this smearing is a source of criticism, or one very important source of criticism for the DJKT solution. So I think you should form your own opinion, but I've always been surprised by this criticism. I don't say I don't sympathize with it, but I'm at least surprised because I don't see a good physics argument right away. Why? Well, recall the way in lecture 1, I actually introduced smearing sources, if you remember. I explained to you that smearing sources is only a formalistic way of saying that the equations of motion you actually solved are the integrated bulk equations. Why? If I integrate a delta function, it's the same as like integrating a finite form, right? Because at the level of the integral, I don't see it. I only see the integrated version. Okay. And solving integrated equations of motion, that is nothing but standard coarse graining in physics, right? I mean, the extra dimension should be small with respect to the ADS scale. So it is fine that if I want to construct a effective field theory, I coarse grain over small distances compared to the distances of my effective field theory, right? So in that sense, I've never understood what is really bad about it. This is why, for that purpose alone, I wrote a purely pedagogical paper with Stephanie Baines. It's a short one. I invite you to look at it in case you want to see these things happening in very simple examples. So I'm just advertising this, and I want to give you a message of this paper, okay? So in this paper, the details are not important, but what we tried to do is to invent the simplest flux compactification we could think of with orientifolds. And the one we found, you know, it's just a detail, but I want to motivate it, is, you know, a compactification with all the ingredients, O6 planes, H flux and F0, and where the tadpole is solved in the usual way, but now the vacuum is 7-dimensional Minkowski vacuum times a torus orbifold. Okay, so what did we find? Because the compactification is so simple, we were able to do many things. We were able to write down the effective field theory, which is completely fixed by some gauge supergravity in 7 dimensions. We were able to write down the full 10-dimensional solution without smearing the sources. Because the solution is so simple, we could actually do it. And we were able to find out the solution with the smeared source. So we had everything on the table to compare the smearing procedure with the actual string theory solution. And what happened, maybe not surprising, you know, intuitively, we found that the smaller we took our string coupling and the larger the volume, we actually had the freedom to do this despite stabilizing quite some modes. We could still do this tuning. The better we noted that smearing becomes. So what do I mean with these words? Here is a picture that should exemplify it, okay? What do I see in this picture? There's a vertical axis and a horizontal axis. And okay, I used a bad symbol. So the vertical axis is e to the phi, the string coupling. And the horizontal axis should be, it should be theta. What I wrote is phi. My apologies, I mixed up Greek letters. So this should be the angle around one of the circles. So the manifold is a torus. So I have 3 circles, and the circles have coordinate which ranges from 0 to 2 pi. Okay. And what I plot for you here, it is a red line, is the profile of the string coupling inside the internal manifold. Okay, this is clearly not coarse graining. I'm zooming into the compact manifold, and I'm trying to understand how supergravity fields are fluctuating. And what do I see? Near 0 and near 2 pi, which are identified, of course, there is a source. The orientifold sits here and here because it's a circle. And near the orientifold, you see that the string coupling goes crazy, but that is normal. It always does that. That is expected behavior. And then in the middle of the bulk, you see it becomes a constant value, some particular constant value, okay? Now, what is a smeared solution? The smeared solution has the constant dilaton everywhere. And what is the value of the constant dilaton? Exactly this line. So what does it mean that the smeared solution is not the same as the localized solution up to it starts deviating the moment I come close to the source, here and here. And what we showed is that the more we fine-tune GS to become small, the larger we take the torus volume, the more this area where the smeared and the localized version differ from each other, the more it shrinks to 0. Okay. So, do we trust DJKT now? That is a question at stake. If you go, you go to Harvard, you ask the people there, they would say no, but it depends on where you are in the world, I think. And therefore, I should say the answer is unclear. And the reason the answer is unclear is because we cannot do this trick. We cannot actually check that the localized picture works. And why? It's for a very technical reason, but now the orientifolds are a complicated setup. So here in the simplest solutions, the orientifold planes intersect according to this diagram. So what do we see in this diagram? The O planes are filling 4-dimensional space. One O plane is, filling the first 3 directions, the second one, the first, the fourth, and the fifth, etc., etc. And if you ask a supergravity person, they will say, oh my God, this is a problem. Why? Because even for a single intersection of D planes in string theory, we almost never have a fully localized solution. So this is very surprising. I mean, intersecting branes, we know from the worldsheet, are all over, they're totally fine. And amazingly, in supergravity, people have failed to find, even for just 2 intersecting D branes in flat space, there are no fully localized solutions. And that's just because, equations are very difficult to solve. So that's a problem. So what does it mean? Either you have some intuition that something is bad about this intersection, or your intuition is more like mine. You think, yeah, but it's probably going to be an argument like this. I am coarse graining and it should always be fine. Okay, you should form your own opinion. At least what is known at a technical level about the would-be localized solution is a mathematical statement by Tomasiello et al. He has written multiple papers. He's very precise. He said, at least I can show that if these orientifolds backreact, the Calabi-Yau will be changed in some SU3 times SU3 structure. Okay. So now the question to ask is, we have this issue. We have DJKT. It's a prime example of a scale-separated solution. KKLT, I will explain, is also getting very close. But everybody is confused whether we should really trust those solutions. So maybe we should try something else. Try something simpler. Maybe we try something without quantum corrections, without orientifolds. Could that work? Well, that's a Sugra question. Okay, so we will check what does 10-dimensional supergravity say about this. Could we do it, yes or no? And then the last thing I'll explain is what do the Swampland criteria say, which as usual are based on some very good intuition with heuristic arguments added to it. Okay, let me quickly tell you what the Sugra arguments say. And this is coming from this paper, which is also a highly pedagogical paper, which with the knowledge you have from these lectures, you can understand from the beginning to the very end. I'm only going to give you the flavor of what is explained in this paper, but it captures everything. And the flavor is that we're going to use, say, 11-dimensional supergravity as an example. And the question I want to ask myself is, can I get scale separation without these annoying orientifolds which start intersecting and we all get confused? And the answer will be no, with a certain assumption, which I invite you to think about, okay? So let me do it. I speak specifically for 11-dimensional supergravity. So that means I'm 11-dimensional gravity, and I couple it to a 4-form field strength, which has a 7-form field strength magnetic dual, okay? And for simplicity of the presentation, I'm assuming no warping. And what do the Einstein equations tell me? This is a thing we have done together in the first lecture. So the trace of the 4-dimensional part of the Einstein equation tell me that R4, the 4-dimensional Ricci scalar, will look like this. So let me explain my notation. You all know what is F4 squared. There's nothing strange about that. There is a 4-form flux inside the extra dimensions. And in front of it, there's a minus sign. So this is a negative number. Okay, why am I writing F7 squared? Do you remember my claim in the beginning? I find it much easier to do calculations in case all the feet of the fields are inside the extra dimensions. Because then the contraction with the metric is always Euclidean. There's no time. So imagine that this 4-form field has 4 feet inside the 4 non-compact dimensions. I can alternatively write this as its Hodge dual F7 field to have 7 feet inside the compact dimension. So that's what I did. So any electric component of F4, I will write as F7. Okay, so this is my formula. So I already see a statement which by now you know very well. Without orientive faults, I have a minus, I have a minus. There can only be ADS vacuum. Okay. What about the internal manifold? I get a plus and I get a plus. And okay, the internal manifold is positively curved. Okay, these are the two things we see. And that is because we don't have negative tension objects. Now comes the link with scale separation. What I can do is I can divide these two equations and integrate them over the whole of space-time, over the whole of the 11 dimensions, right? If you are very careful about this, you will see that if I do the integral on both sides, the integration over the 4-dimensional part here cancels against each other in the numerator and the denominator. And so I get all of these positive terms. It's a little algebra to show that this ratio will always be smaller than 5/4. It's not difficult, just try it yourself, okay? Good. What does that teach me? What is the link with scale separation? Well, I can give you the intuition, okay? Take some internal manifold that is a sphere. Now try to shrink the volume. What does that mean? It means that the curvature becomes very large, right? Because a sphere with small volume is highly curved. So R7 should blow up. And if I want to shrink the volume at the same ADS scale, that means that R4 has to stay constant. So scale separation would imply that these numbers should become very huge, but I find that it's smaller than 5/4. Okay. Let me try to do this once again in a bit more careful language. Let me define a thing I call the curvature radius. The curvature radius is defined as 1 over the volume times the Ricci scalar integrated. Similarly, the ADS radius, I could define it as 1 over the volume of 4-dimensional spacetime, which is of course infinite, times the integral of the 4-dimensional Ricci scalar. And when these two infinities cancel each other, you get a finite number. Okay, so these are the two, what you could call curvature radii. And what we just showed is that the curvature radii cannot be decoupled. I cannot make the ADS curvature radius as large as I want, meaning very small curvature, versus the curvature scale of the internal manifold. This would be a full proof of a lack of scale separation on one simple condition, on the condition that the curvature radius is a good measure of the Kaluza-Klein radius or the Kaluza-Klein scale. And that is something you can completely disagree with. Okay, and I have no problem, but I invite you to find a counterexample on a manifold that is positively curved with a positive definite Ricci tensor. These are very simple mathematical questions that I'm asking. And what is beautiful about the Swampland program is that this is now being investigated by mathematicians. So what is great, I think, in the whole of science, if you have a new paradigm, what a paradigm often does, it allows you to ask questions which somehow we never thought of, and they could be very simple questions, right? So we in string theory or people looking at extra dimensions now have like a trivial question which I could have answered, as a bachelor student with a basic knowledge of GR or of differential geometry, and surprisingly, we mathematicians haven't properly thought about this, right? So that now even have been papers by some mathematicians who are, because of this, studying this question. Okay, so I think it's very exciting. And shows why the Swampland is a sort of a very healthy direction to work on, because it inspires other questions in other fields of science. Okay, so that's a question I'm asking, right? It's often the case, but maybe not always. And if it's not always, you could actually find a scale separated Freund-Rubin solution, right? So imagine that it does, we actually get an extension of the Maldacena-Nunez no-go theorem, right? So what I'm going to tell you now is let us for a moment assume that the curvature radius actually measures the Kaluza-Klein radius. Let us assume that. What I then have proven, I mean, okay, I can do it in general. You can find it in this paper. Within that assumption, we can make the following proof. If I compactify on a static, smooth internal manifold with flux and only positive tension branes, I have no de Sitter, I have no Minkowski. This is known as the Maldacena-Nunez theorem, and I have no scale separation of ADS. So you should think of the last bit as an extension of the Maldacena-Nunez no-go theorem to anti-de Sitter space. So what are the ways out? Clearly negative tension objects. The moment I add them to my calculation, I cannot make the claim. And that's, of course, what DJKT was saying. Or quantum corrections together with orientifold planes. That is all the other string pheno setups. KKLT, large volume scenario, etc., etc. Okay, what is a Swampland saying about this? What are the conjectures? There are many, and I decided to only present a subset of the original one, just to give you a flavor. And all the rest, all the other related conjectures are very, very technical, much more detailed also. But the main one is this. It comes from Lust, Palti, and Vafa in 2019, and it goes under the name of the strong ADS distance conjecture. It's something that applies only to supersymmetric ADS. And the claim would be that the Kaluza-Klein scale is always or order 1 times the ADS scale. In fact, they were more precise. Here I'm a bit imprecise. I say Kaluza-Klein. They just say any tower of scale. And Kaluza-Klein fields are a specific tower of fields that UV complete a theory. But string theory has other towers. You can have Kaluza-Klein towers, you can have string winding states, etc., etc. So what they wrote is the cutoff scale of the theory is order 1 times the ADS scale. So if that is true, I mean, it's an amazing statement. It means that there will never ever be an ADS vacuum that can be described within effective field theory. It's always fully 10-dimensional. Where does the logic come from in this paper? Well, what they did, a little bit heuristic, is they said they extended the idea of the distance conjecture, which I think you have had lectures on. For scalar fields, they extended this to distances on metric space. And when you do this, you seem to get something like this. But this is, of course, heuristic. The distances on metric space are not really clear. And it's also not clear why the distance conjecture should be extended to other fields than scalar fields. But imagine the conjecture is true. Personally, I think this is the wildest Swampland conjecture that exists. Everybody sort of was amazed by the de Sitter Swampland conjecture. I never understood why people were so amazed, because it's only an asymptotic statement. This one is an extremely strong statement. And if it's correct, it essentially says there is an issue with almost all of string phenomenology that we did in the last 20 years. Why? Either all those papers are wrong, or some bits of it are correct, but you can never take the fine-tuned limits. Okay, so for sure there would not be a landscape of 10 to the 500 semi-realistic vacuum, not at all. All right. So how does, I discussed DJKT at least very roughly. How does KKLT go about and do it? Okay, I'm just going to sketch it. You might have seen this before. So KKLT is based on GKP. That's a solution I presented in lecture 2, last lecture, the previous lecture. But you remember I said the Kähler moduli were flat. Of course, it would be strange if they are flat at the quantum level. That would really require some bizarre non-renormalization theorem, which actually doesn't exist. So we know for sure there are no flat directions. There will be quantum corrections. And the whole difficulty of string phenomenology is, can I get a handle on these quantum corrections? Can I compute them in a way that I understand them? Okay. KKLT suggests, let us for a moment, just for presenting simple calculations, assume that we only have a single Kähler-Calabi-Yau geometry, just for simplicity. There's only one Kähler modulus. I'm going to call it rho. Rho is a complex modulus. So the imaginary part is measuring the volume of a force cycle, the only force cycle. And the real part is the corresponding axion that you get from integrating the C4 field over this force cycle, okay? And they argue that either from instanton corrections or Gaugino corrections, Gaugino condensates, sorry, coming from 7 branes wrapping this force cycle, there must be a non-perturbative correction of this kind. So there's a number A, which is called a Pfaffian. It can depend on the complex structure moduli, but you remember W naught, which is the Gugo-Pfaffa-Witten piece that we discussed last week. It's this thing here that we discussed yesterday. It stabilizes, we think it stabilizes a complex structure moduli at a high scale, at a string scale. So they're effectively frozen, so you can think of this number as a constant. Okay, good. Now you can solve this equation as well. This equation we didn't solve before, but it was not necessary to get a solution to the equation of motion. So this means that we can actually solve the last F term condition. So amazingly, we can find SUSY ADS vacuum. Okay. Yeah. Did I give the value of the, here I gave the value. So if you want to check, I think I made a typo here. There should be somewhere W naught squared and I'm not seeing it. So my apologies. I think what you have here in the denominator is W naught squared. So if you do the calculation, it's actually not difficult. Okay. So this is just a calculation of 1 minute. You just need the form of the Kähler potential, which I didn't show you, but it's in any textbook. Then you find that this gives an ADS solution of the following value. So T naught is the stabilized scalar modulus. Here is the volume of the force cycle. Little a is just a numerical constant, and a is this Pfaffian, and there's a 1 over W naught squared, right? So, so T0 is a solution to the F term equation, which you can rewrite as this. Okay, good. So what is highly non-trivial about this, I should already tell you before I explain you the debates about this. Something very strange happened, right? We had a solution. We had a classically a Minkowski solution. We also noticed that the moment W naught is non-zero, this was a non-SUSY Minkowski solution. We find that the flat directions are lifted by quantum corrections. That is not bizarre at all. But after the lift, the non-SUSY solution turns into, the quantum correction turns into a SUSY solution. That's a highly non-trivial thing that happened. And so there have been huge amount, like already since the birth of KKLT, people have been debating it. And the debates of the last couple of years have been the following. For this to be consistent, just look at the equation. You can tell there's something very bizarre. What is this equation saying? This equation is saying that I'm balancing a non-perturbative quantum effect against a classical flux source. And whenever you do physics, I mean, if there's a ball rolling down a hill, you're never going to say that a non-perturbative quantum effect can make the ball stop, right? So this is a non-trivial situation, but okay, they say it happens, you can do the calculation. It happens if my classical force is very, 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 very tiny. So clearly, W naught needs to be very small, fine-tuned. The debate is, can we do this? Okay, I invite you to look at the archive. There are like tens and tens of papers discussing this. Yes, no, I mean, it's highly technical, but at least I want to show you where the debates are. So that's one series of debates. Another series of debates I already explained you before. We assumed that we can stabilize all the complex structure moduli, and they will give us a finite value of W naught and A. And you know, the rest is scalar moduli stabilization. But I explained to you that there was a tadpole conjecture, which is telling us that for a generic Calabi-Yau, that is actually not true. Also, this is a debate. Not everybody would agree with it. Another debate is whether we should even trust this approach from the very beginning, right? Because was I doing top-down string theory? No. When I say the word Gaugino condensate, it means, okay, there's some 7 branes. I run to the IR. You know, the gauge, the Young-Mills fields go to strong coupling. They confine. That is a non-trivial Gaugino of F. And then you need to figure out, okay, how do I incorporate that into my effective field theory? But clearly, that is sort of top-down, bottom-up arguments in between. This is not a clean string theory calculation. Okay, so that's also a debate. And the final debate, which is more relevant to my previous lecture, can we uplift these solutions to the Sitter space? I've worked on this for a long time, but if you want to know what is the upshot, I don't want you to look at the works I did. It's only very recently that I think that finally an actual problem has been found with the uplift. I cannot explain it, but this is a hugely important paper. It's by Hebecker et al. From 2019. This is the archive number, and they actually find a problem. If I would have had time for a fourth lecture, and it's my problem that we didn't have the time, is not yours, I would have happily explained this paper because it's not so difficult to explain. It's surprisingly simple, in fact. What I maybe can say something about in the last 3-4 minutes is something about debate number 3. Should we even trust the whole approach? Okay. And there are many ways to approach this. And what I personally think is extremely exciting is the holographic direction. So holography, I mean, if all of these dreams of KKLT are true, holography should be able to tell us, right? Because it's an ADS vacuum, holography works, so there should be a dual CFT description. Is that true? So one of the most crude things in the dual CFT we can look at would be the operator dimensions of the operators that are dual to the scalar fields in the effective field theory, right? And such operators would be single trace, scalar primary operators. Yeah. And by now there's a famous formula for what operator dimension should be. They are 3/2 plus 1/2 times the following square root. 9 plus 4 times the mass of the scalar field times the ADS length, this to the power 2. So this is a dimensionless number. It's mass times length. So this is indeed just a number without dimensions, right? Okay, what is now special about phenomenological ADS vacua? Different from, say, ADS 4 × S7 or something. If you trust KKLT or DJKT or whatever, they say, oh, in my effective field theory, there are only a few scalars which are not super high in mass. So these are the scalars of my effective field theory. There are a few. Also, their masses are positive. Why is that important? Because in ADS space, it's okay to have tachyons, which are not too tachyonic. But if you want to lift the solution to the sitter space, it better be without the tachyon. Okay, what does that mean? So it means that these M's are small enough. They're positive, but you see, the moment there are no tachyons possible, you will see that all the operators are either marginal or relevant, right? I mean, if M would be 0, I get dimension 3. It would be a marginal operator, which you can have in a SUSY CFT. But what KKLT was, for instance, would be saying is no, there's like a few, mass scalars where this is, say, order 10. And then there's a huge gap. And then the next states would be Kaluza-Klein or stringy states, right? So they have in mind the existence of conformal field. If I translate this holographically, there would be conformal field theories, which are what you would call a dead-end CFT. What does that mean? There are no relevant operators. So it is impossible to flow out of this CFT. These CFT are sinks in the RG landscape. This is why I call dead-end CFTs. They're only attractors. And there are only a few low-lying irrelevant operators. And then there's a gap to irrelevant operators of huge dimension. I mean, there's never, ever a CFT being written down that has that property. Does it mean they don't exist? No, but it at least shows that all of these claims in string phenomenology predict something in a conformal field theories which has never been observed or even dreamed of by conformal field theorists, right? So I think I seem to be getting out of time. What I wanted to tell you quickly about are some recent results in this field. Do I have time to say this? Probably I should. Let me quickly try. And then I go to the conclusions of my lectures, okay? So in the most recent paper by Lust et al., which I think is extremely striking, they actually show that they cannot find the dual CFT to KKLT. What they can find, or claim to find, I mean, this is an amazing paper, and if true, is a huge revolution. They claim to have found a QFT so somewhere here, that would flow to the CFT if it exists. And what they can do in this QFT is they can count roughly the number of degrees of freedom in that QFT. That means that they can sort of count what you would call the would-be C function or central charge. But you know that if I flow to the IR, degrees of freedom are always getting smaller. So they can actually bound the central charge of this would-be CFT. You could say, who cares? Well, according to ADS CFT, there's a clear link between the central charge and the size of ADS space. Size of ADS space is like the length is L squared of ADS. Sorry, the central charge equals L squared of ADS. And what did they find? They actually could bound this number by a small topological number, like order 100, 1000. But you know, for a phenomenological ADS space, this would need to be billions and billions in string units. Okay. So they say, how can ever KKLT be correct? Because we can bound this number to actually a small number. Okay, this is more technical. Let me just go to the third example because I'm biased. This is I also wrote a paper on this. Instead of KKLT, people also looked at the would-be holographic dual to DJKT. We have no reason to say it's inconsistent, but we did. There's some huge surprise, which at this point in time, I do not understand where it comes from. What we found, first observed by Conlon, we only generalized it a bit, is that for an unknown reason, all the conformal dimensions are integer. And this is just, I want to give it to you. It's out there. We don't know what it means, but try to appreciate how non-trivial it is. Look at this equation. You know, why would the combination of MLADS be such that this whole expression with the square root gives you an integer? There's no reason. Yet we get that. So that, to me, this is exciting. It means that, you know, if somebody can ever, you know, try to look like a more expert person in conformal field theory might say, oh, there's a very special CFT predicted. Not only does it like dead end, etc., etc., it has only integer conformal dimensions with n equal 1 supersymmetry, which is highly non-trivial. Okay, this might have been a bit technical, so let me go to my conclusions. What did we do? I showed you, this was the angle of my lectures, that lots of the DS and ADS Swampland conjecture can actually be argued for in 10-dimensional supergravity. But the difficult part is to move beyond that limit and try to argue that they are correct. And I ended by saying that I believe strongly that the most promising direction is that holography can help us with this. I skipped millions of things. Most important thing that I skipped that I wanted to explain was anti-brain uplifting. I didn't get to that. I also focused a bit on KKLT instead of many of the other creative ideas to stabilize moduli, like large volume scenario, and many others. There's also something exciting happening recently with brain world scenarios. I also didn't explain to you the TCC conjecture, which is very strongly related to the Swampland conjecture for the Sitter space. Thank you very much for listening.
Thank you very much. We have time for questions, please.
May I have a question?
Yeah, sure.
Thank you, Thomas. Very nice lectures.
It was my pleasure.
I guess this holographic argument cannot be immediately applied to large volume scenarios because we don't have this first ADS construction and then uplifting, right? So are there some ideas on can be applied?
So Conlon actually wrote papers on this, also Fernando Quevedo, which you might want to look at. So, well, you don't need to uplift to the Sitter space, right? So, but I'm not sure you were asking this. So this is only about the consistency of the ADS vacuum prior to the uplift to the Sitter space.
Exactly.
Right. So the only little bit of problem that you could argue with a large volume scenario is that it's non-supersymmetric ADS. And then, of course, there's a claim by Oguri, by Vafa, and also by others that, well, if ADS space is non-SUSY, at best it is metastable. And then you get in trouble because what is holography for metastable ADS vacuum? I think it's also an exciting question in holography. People should try to find an answer to. But at the moment, we don't know how to do holography for metastable ADS. And why is that? If you want to go to the boundary of ADS when it's metastable, ADS is breaking down. And in fact, the nucleation rate of decay is becoming 1 when you approach the boundary. So you cannot talk even about the boundary, right? Also, think about it very naively. If an ADS space is metastable, it carries a time scale, namely its decay time. But a CFT by definition doesn't have any preferred scale, right? So,
yeah, I thought we must have some kind of scale separation problem in DS construction right away. Like in larger scenarios, we have we don't go through ADS construction first. We immediately do DS construction. And
no. The original paper on LVS was constructing ADS. In fact, when Joe Collin gives a talk, he's one of the authors. He always says, "I don't want to discuss going to the sitter. I don't know how to do that."
I see.
But it's true. Many cosmology papers write in such a way that you think they immediately jump to ADS, to the sitter, but that is not true. So if they want to go to the sitter, they should probably add an anti-brain, some warp throat, etc., etc. Yeah.
And the other point that you brought out about anti-D3 brain uplifting, I guess, it's all about the second stage, right? How we uplift, and there's a problem, right? We have this kind of, I wouldn't say, runaway problem, right? We cannot get a bottom modulus stabilized.
So it's amazing. I mean, this field this topic of criticizing anti-D3 uplifting is super old, and you should know. I mean, I worked on it for a long time, and I have to honestly admit that people have been saying it doesn't work, and then it actually did work, and it has been jumping like this. And it's only now that I think in 2019 that Hebecker found a completely orthogonal problem, which is highly non-trivial. And it's not really a runaway problem. It's more that you can actually show that if you want to prepare an ADS vacuum that is suitable for uplift, you can actually show that that solution is completely out of control. At the ADS side, it means that somehow, roughly speaking, the D7 brains that are involved in this setup must backreact all the way into the throat. And that means that there's no decoupling between the SUSY breaking modes and the SUSY theory, but they should decouple, otherwise you have no control. Yeah.
Yeah, I wonder how Stanford people receive that. Because I remember that long debate between, this uplifting in supergravity picture. Linde argued that there is no problem. I remember some of your papers.
Yeah.
Other papers that we cannot even do that in supergravity because we have this superpotential term that destroys everything. Yeah.
Right. Well, I think a lot of the old debates all had to do with singularities that form at the D3 position, at the anti-D3 position. But then it was Polchinski and so Polchinski had an argument in string theory why they should be absent. And then we actually did the supergravity calculation to show that in the end, these singularities are absent. So in my opinion, they're not a problem anymore. That debate is, in my opinion, solved, but maybe Yossi Bena or somebody else would disagree with this. So you should talk to them as well. Yeah.
Thanks. Just before I go, a short announcement that Thomas very readable lecture notes are now uploaded on website. I put the link here. Everybody's interested, you can go and download these lecture notes. Thank you, Thomas.
It was my pleasure. Thank you so much. I see there's still one. No, you put the chat. Yeah. Okay.
Yeah. Any other questions?
Excuse me.
Yeah.
Excuse me. So I just wanted to ask, aren't there any possible proofs or at least convincing examples about two-seater conjectures locally and not just asymptotically?
You mean the
so that the gradient of V over V should be greater than number and the
no, because the TCC, I mean, okay. So first of all, I wouldn't know an argument, right? Maybe the only argument would be that I don't think there's any de Sitter's construction so far in string theory from a compactification that is successful. You could take that as an argument, right? But it's not that strong because maybe, humanity is just not good enough at trying to find one. But I don't know of an argument, like a heuristic argument, that would be able to extend it to the middle of moduli space. And in fact, the only conjecture I know that exists in the middle of moduli space is the TCC conjecture by Bedroya and Waffa. And that conjecture does allow metastable de Sitter, right? So the critical, well, yeah, so it would violate literally these inequalities.
Yes, so I was confused because at least in the main papers about this topic, the conjecture was, I mean, stated as if it's locally correct. So
Yes,
it's not.
you are right.
Like
Yeah, I'm happy you make the remark. You absolutely have a valid point. So it must be highly confusing to the people trying to go through the literature. The original paper made a claim, just very brave. It's everywhere true. And it's only the second paper that said, oh, okay, let us be more careful. And then they say, look what we can argue for in the asymptotic limit. And then there was a TCC paper by Bedroya and Waffa. And if you read it, you realize that, you know, they're willing to speculate that indeed the Swampland, the original Swampland conjecture is everywhere true, but they say, let us take a step back and formulate something which is more careful, which is the TCC conjecture. Yeah.
Thank you. Thank you.
Thank you for the remark.
Okay, any other question? Okay, I don't see any other questions. So thank you very much, Thomas, for devoting time for very great lectures. And we hope to see you in person in Tehran very soon in our
I would very much like that.
Thank you very much.
Absolutely. Thank you so much.
Goodbye.
Have a good day. Bye-bye.
Bye for now. Bye.
Bye-bye.
So we'll be back in 15 minutes.